But nuclear stability is a concept that explains exactly what it sounds like. How stable is the nucleus of any isotope that exists? And if you think about it, if I have here drawn a nucleus, and in here in the circle, I have some protons and neutrons. What I know about the protons in my nucleus is like charges. So my positive protons, like charges, are going to repel. So if you think about it, no matter what the atom is or what the isotope is, the nucleus, you would think, should be unstable for a lot of, well, basically for everything out there, because anything with lots of protons, if like charges repel, then the protons are they're not gonna want to be very close to each other. However, not everything is not every nucleus is unstable. So why are some nuclei actually stable? They're not actually going to have the tendency to repel or break apart. So the first thing is the presence of neutrons. So we know that neutrons, which do not have a charge, neutrons help to stabilize the protons in the nucleus. So the presence of neutrons helps to stabilize the nucleus. Okay, and that would make sense because you have another particle in there, a heavy particle, that can sort of balance out or help keep the protons together and not repel and totally decay. So that's great. There's another concept that helps me to keep the nucleus totally together, and that's something known as a strong nuclear force. So a strong nuclear force, if you research online, you'll see there's not a ton of information about strong nuclear forces and what it exactly is, but it is another concept that minimizes repulsion. So this strong nuclear force, its job is to minimize repulsion of protons, and therefore it helps to keep the nucleus together. And again, it helps with nuclear stability. So once again, let's just sort of highlight the two concepts that help keep a nucleus stable. Number one, I'm sort of doing my notes off the top of my head here, so this is a little bit all over the place, but number one, the neutrons. So the neutrons help to stabilize my nucleus. And then number two, this strong nuclear force, which again, we don't understand too much about, that also minimizes repulsion and stabilizes my nucleus. Okay, so that's great. That helps to explain why many nuclei will stay together. And one more thing we can consider for nuclear stability, I'm going to change the slide here, is something known as a neutron to proton ratio. So a neutron to proton ratio. And what we know, again, about stable isotopes is that if you're a small element, if you have a small atomic number, so let's say if your atomic number falls between 1 to 20, then if you're going to be stable, you will have one neutron to one proton. So the ratio is 1 to 1 if you're a small atomic number. Now, if you're a larger atomic number, so basically anything bigger than 20, the ratio of stability is actually 1.5 neutrons to 1 proton. Okay, and so again, these ratios this would be a stable isotope. So think about this logically for a second. This would make sense because if you're a big atomic number, you have lots of protons in your nucleus, lots of protons. So therefore, you would need more neutrons in your nucleus to help stabilize you, as well as a strong nuclear force. Those things would keep you stable and not decay. That would prevent you from breaking apart and releasing radiation and releasing alpha particles and so on if you are a large element. So for example, if I have this element, this isotope of lead, 206 over 82 ppb. So this is, remember, this is one isotope of lead. There's many different isotopes. If I do a little bit of counting of my particles here, my atomic number is 82, so that means I have 82 protons. The electrons don't really matter, but I also have 82 in this neutral atom. And then my neutrons is going to be 206 minus 82, and that'll be 124. Okay, and if I actually look at the ratio between the neutrons to the protons here, so if I divide 124 divided by 82, I think I get 1.51. And so this would actually be a stable isotope of lead. Because it falls into this ratio. And what that means is what that means is that lead 206, if it's stable, that means it doesn't break down, it does not undergo nuclear decay, or it's not radioactive, it's not a radioisotope. It'll be pretty stable and stay as lead 206. It'll just stay like that. Okay? And on your lesson handout, I'm going to switch over now to a different slide. You have a graph. I don't know why this one's so huge on the screen. Sorry, I tried to make it smaller. But anyway, you have a graph that looks like this that sort of summarizes everything we talked about. So if you are a small element, I'm going to try to highlight aspects of this graph, okay, so you guys can see what I'm talking about. So if you're a small element, for example, atomic number 20, so notice on your y-axis you have neutrons. So neutrons are on the y-axis and protons are on the x-axis, okay? So if I'm atomic number 20, if I look over here, so 20 is if my atomic number is 20, and I also happen to have 20 neutrons, I'm going to look at this intersection on the graph. Then what's my ratio, or my neutron to proton ratio? Well, what I just highlighted here in that intersection, 20 divided by 20, that's a 1-to-1 ratio. Okay, and so if I'm this element and this isotope right there on this red line, again, that intersection, again, let me try to highlight that, or you get the idea, but if I'm like right there, I would be a stable isotope of, that's calcium, right? Atomic number 20. So that would be a stable isotope. It's not going to break down. If I go a little bit higher on my graph, if I go up here and I say, if I have 80 neutrons and I have 60 protons, again, let's find that intersection point. Then I'm a bigger atomic number, and my ratio, if I go 80 divided by 60, it's close to 1.5. And again, if I fall on that red line, I'm a stable isotope of that, whatever element that is. You can look it up on your periodic table, element 60. Okay, so that's great. But what if I'm a different isotope and my ratio is off the 1-to-1 or the 1.5-to-1? Well, in that case, I'm going to not be stable, and I'm going to actually undergo nuclear decay, which means my nucleus is going to break down. So for example, if I fall in the green region where it says beta, so if I'm an isotope and, so as an example, if I have 100 neutrons, and if I have, I'm just going to make up any fake point here, if I have 30 protons, okay, so if that is, I don't even know if that's a real element, but or a real isotope, let's just pretend it is. If I'm that intersection point, my ratio of neutrons to protons is off, and that means my nucleus will be unstable and it will undergo something called beta decay, which explains in the PowerPoint more about that. Okay, if I fall into this region, then I'll undergo alpha decay. And then if I fall in the pink region, I undergo electron capture or emission. And, those points are not so important, but gives you an idea that there are different kinds of decay as well. And these nuclear decay types we're talking about, they're radioisotopes, so they release radiation, like an alpha particle, which you may have talked about in physics. Those are released, or a beta particle, for example. Okay, and some are more dangerous than others because some types of radiation can actually penetrate the human cell, but then other types can be blocked by like a sheet of paper. So that's a lot more detail, but I hope that makes sense about nuclear stability. So I'll go back to what we started with, and what makes a nucleus stable. So it's the neutrons and the nuclear force. And basically what happens if a nucleus is not stable, that means it'll break down. The nucleus will break down using either alpha or beta decay or gamma decay. And we can look that up on a graph by looking at that ratio as well. All right, so this additional content hopefully will make sense. And I'm going to do a part 2 now of the video to answer the question about half-life. So that part definitely refer to, because that's part of our normal content, but also half-life will be part of your AP exam as well, if you choose to write that exam. Okay, so this is, again, where you have to kind of mentally organize the information that we're looking at, and decide, what are the AP components and what are the regular components, okay? So stay tuned for part 2 if you need to see those examples, and good luck studying.